Okay, just in time. Hello everybody, welcome back to our C++ course. I'm very happy that you are still here. It's always a pleasure to see students coming back. I refer to myself as a programmer, and that's even while I'm a professor at the computer science department. And that might be strange because the term programmer has disappeared a long time ago in public use. Even if people like Dijkstra or Ken Thompson or other big luminaries in the history of computers have referred to themselves as programmers. Nowadays, people usually tell you, no, I'm not a programmer, I'm an architect, or I'm a computer scientist. And let me tell you that most of those people, and I know that I will insult them heavily, most of those people have never written a single or a serious amount of code in their lives. And by serious amount of code, I mean tens of thousands of lines of code. And that's not different here at the computer science department at LSU. Most of those professors are very bright theorists, but they have no idea how to write code. So what my goal for my work is to be able to write code that is correct by design. So when I write code, I want to understand the code. I want to be able to understand why it's correct, and I want to be able to assess that it's correct just from looking at the code. How do I do that? Or how, it's not just me, obviously. Many people strive for that goal. If we want to achieve that, we have to understand certain theoretical aspects of programming, and I want to talk about that today a bit more detail, a bit more from the theoretical side. If we look at the structure of the C++ standard library, and I will talk about the C++ standard library in 2 of the upcoming lectures in more detail, they go back to the very first slide I showed you in this course, in the very first lecture, namely to the thesis that programming equals algorithms plus data structures. And that C++ standard library kind of embraces that concept to the fullest. When I talk about data structures, I mostly refer to those data structures as being containers, so things that can store more than one element or more than one instance of a particular type, like a standard vector, right? You can have tens of thousands of integers in that vector. And from the standpoint of algorithms, it's those functionalities that allow us to work with those containers and do certain operations on the containers. In the simplest case, just a for each. Do some operation on each of the elements of this thing I'm giving you. In order to analyze data structures and containers properly, we have to understand what are the properties of the thing I want to store in my container. If I have a vector of int, we know that it just works. So what are the properties of that int that make a vector work? Or even more, if I have a vector of vectors of ints, does that property of int transitively is inherited by the inner vector so that the outer vector can store the inner vectors? So we will talk about what is a type today, what are the properties of types that make all of this work nicely. It gives us, when we start understanding these properties, it gives us a nice security, if you wish, or the certainty that as long as a type has certain properties, we can be sure that we can store it in a vector, we can store it in any of the other containers, but we also can apply any of the algorithms that rely on those properties to be true without having to reason about it, and we can be sure that things work properly. So as I said, what I want to do today is to talk about these elementary properties a bit. But in the beginning, I want to start with just a definition. What is a type? What are types? And by extension, what are objects? Because people often are unsure about the distinction between what is a type and what is an object. We will talk about patterns for regular types. I will develop a C++ class which is as simple as it can get, but as complete as it can be. And that C++ type, which I call the Singleton, you can use for your future life whenever you want to create a user-defined type. Just use that thing, rename it, and add all the functionalities you want to add. And you will have a type that can be stored in any of the standard containers. And you have a type that you can use with any of the algorithms in the standard library. Later on, I will introduce another first derivation of Singleton, which I called instrumented. It's a special type that not only conforms to those properties, but it also counts the number of operations applied to that thing. And that will allow us to go back to the claim I had in the first lecture, namely that finding the unique numbers in a sequence of integers can be done by storing them in a set, or we can apply a standard algorithm. We can sort them and then call unique on the sequence. And my claim was that the second way of doing things is much faster than doing it by storing it in a standard set. And we will kind of try to analyze why that is the case. Okay, so what is a type? Anybody here? If I ask you, what is a type, how would you define it?
Not really sure. I don't know what C++ that much.
Well, types are in other languages used as well. Java has types.
I mean, I guess like different ways to store different types of variables.
Okay. Other ideas? I mean, you have been working with types, right? Java is kind of the must here at this university. You any idea? How would you define a type? No? No idea? Please.
I guess it's like a description of how a variable should and can be used.
Okay, very good. That's the first. Comes close. What else? Karami, you're smiling. You know it. Okay. Want to say something?
It says what is stored, what type of data is stored, and what operation can be done.
Okay, that's very close to what you said, right? What operations can I apply to a certain thing? But most fundamentally, a type is how much memory do I need to store everything that is related to that thing I want to store? How much memory? The second thing is, memory is always bits. And if I give you a bit pattern, let's say just a byte, single byte, 1 0 0 0 1 1. What is this? Is that a minus 125? Is that a plus 131? Is that something completely different? What is it? So a type gives us the rules how to interpret the bits that are stored in memory. Because in the first case, we interpreted that number as a signed integer or a signed char. And here we interpret it as an unsigned char. Right? Two different types, same bit pattern, gives us different results. So a type is how much memory do we need? How do we interpret the bits in that memory? The third is, what is a set of values I can represent there with those bits? And last but not least, what operations are valid on those bits? And that's it. So that's the four things that define a type. And it's very important to understand that, because we talk about types all the time, but do we really know what it is? Well, it's these four things. It's the amount of memory, It's how to interpret the bits. It's the values we can represent with those bits. And it's the operations that are valid on those values. Okay. Well, examples of types, obviously, the built-in types, integers, doubles, floats, chars, you name it. But also all user-defined types like std_vector or some other user-defined types, which I just pulled out of thin air, token or token stream or whatever, are user-defined types. And each of those have those 4 properties. Okay. So what is an object? Java is an object-oriented language. You have been working with Java, so you should know what is an object. How would you define an object? Any idea? Anybody? Yes?
Would be like an instance of a class.
Absolutely. It's an instance of a type. It's one thing that is instantiated that represents that has a type usually. Well, in Python, even if Python is a typeless language, typeless in the sense that a variable doesn't retain its type over its lifetime. You can assign different things to that variable. At a particular point in time, each variable represents a certain type, even in Python, in those weaker type, unknown type languages. So what is an object? It's a thing that occupies memory. It requires memory to be stored. It has an optional name. It's a variable, right? You give it a name as a variable. By the way, why did I say optional? Anybody? Can you think of an object which has no name? You're nodding. Temporary objects. The things that are returned from functions have no name, but are still objects, right? If you have a function that returns an integer, that integer doesn't have a name. You can't directly access whatever is returned from the function. You have to assign it to a variable before you can refer to it, right? So it's a temporary object. In C++, you can create temporary objects in other contexts as well. And most importantly, and that is crucial for C++, an object has a lifetime. It starts its existence at a certain point in code, and it ends its existence at another point in time. And if you have ever written C code and have returned a pointer to a local variable, you know what I mean, because you probably had a segmentation fault when you were dereferencing that pointer, because a variable has gone out of scope at the point when you actually use a pointer. So be aware of when does the lifetime of an object actually end. And this is a common problem at least in C++. In Python or in Java, it's not that much of a problem, because in Python and Java you have garbage collection. You have a system that makes sure that the variable stays alive as long as somebody refers to it. So there you usually don't worry about lifetimes. But in C++, it's a thing, and we have to be aware of that. So objects in C++ do not change their types. The type of an object in C++ is defined at its definition, and it stays that. And the type safety, or the amount of the operations you want to apply to a particular variable, are checked at compile time, whether that type supports that operation. Well, examples of objects: simple integer, simple token, which here is initialized by a plus, or a vector. It's an object. Okay, now type regularity. If we think of what can we store in a vector, we know that we can store an integer. We know we can store a double. So what are the properties of integers and doubles that make it usable in the context of storing it in a vector? And what we will talk about now is a concept, regularity, because regularity is what, well, you can't just say everything that behaves like an integer is regular, okay? So in the simplest case, if we informally define regularity, we will say, well, it behaves like an integer. That's fine. So if you create a type and it behaves like an integer, you can say it's regular. But let's be more rigorous about that a bit. It's obvious that regularity defines a set of properties a type should have. And it's important, as I already said, to understand these type properties because it will give us an understanding what are we allowed to do with those things. Can we store them in a vector? Can we store them in containers? And can we apply, what algorithm can we apply to them? We will use a term here, which I call, well, not I, people have called concepts. Whenever you hear the term concept, it's a set of type properties that describe a certain thing. And in C++20, so the language we're using here, language features we have available to ourselves, you can define a concept in the language. You can say this type has this property, and you can check whether a certain type exposes that property in the language. And we will use that to constrain the use of our singleton object in a moment. So let's start with something not as strict as regular, but as, let's call it semi-regular. The one thing a semi-regular type should have is what C++ calls a copy constructor. It's a bit weaker than regular and exposes a copy constructor which has the following semantics. You can create a new object of type T called A from another object of the same type B, and after that you initialize A from B. And the second option is that you can assign it at initialization time. And these two things are actually the same in C++, as long as B is the same type as A. So what are the semantics of this operation? What would you expect if you see this code? Well, slide says it already. After this operation, A should be equivalent to B. What is equivalence? What does it mean for A to be equivalent to B? Well, in the simplest case, in the math, from the math standpoint, equivalence is a relation R between A and B. And it's true as long as these three properties are met. Namely, it has to be symmetric. That means that if A is equivalent to B, B is equivalent to A. It should be reflexive. So every object is equivalent to itself, obviously. And transitive, the usual triangle rule, that is A is equivalent to B and B is equivalent to C, then A has to be equivalent to C, obviously. As long as these three things are true, you have an equivalence relations. And we will talk about that more in the future. But equivalence is not sufficient. What we actually want is equality, which is equality is an equivalence relation which has additional properties. In the simplest case, you can think of equality of a type has equality defined as long as it has an equality operator defined. So if you can write A equals B, then A equals B should check for equality of these two things, whatever equality means, right? There could be several definitions of that. So if A is copy constructed from B, they have distinct identity markers. In other words, they sit at different positions in memory, so they have different addresses. They are still identical. If I copy an integer 42 to another integer, the value of the integer is the same, right? So these two things are equal. So our equality operation will return true. So all copy constructors must behave this way. This is one of the rules of semi-regularity, that all copy constructors should ensure equality of the objects involved. So if somebody comes along and tells you, hey, I wrote a nice copy constructor which does something magic and which doesn't create a new object that is equal to the other one, send them away. You don't want to do that because that breaks the world. Everything perishes if you do that. And the reason is that you cannot reason about your code anymore. Well, there's one exception when you want to do that. What is the exception? When do you want to do something weird like this? Anybody? If you want job security. You write code nobody else can understand, so nobody can fire you, okay? So then you can apply these tricks. But then be careful to remember what you actually did, okay? So while it might work and the compiler might be happy, you get a program that doesn't do what the people expect from looking at the code. The second thing semi-regular types have is an assignment operator. So you can write, you declare a variable A without initializing it, and then you assign a variable B to A, and after that you get an object which is equal to the former. Obviously, construction with initialization, so creating an object from a new object A1 from B, should be completely equivalent to creating a object through assignment. Now the question is, what's the difference between initialization and assignment? Anybody? This is initialization. This is assignment. What's the difference between the two? Think of T being a vector of integers. So I have one vector of integers here, and I initialize it from another vector of integers. And here I have a vector of integers which is empty, and then I assign a new value to that one. What's the difference between the two operations? Are they completely the same, or are they slightly different? Anybody?
The initialization is kind of like creating a space in memory vector, but you're not saying anything about the contents of that space in memory, or maybe you're just zeroing it or there's assignment here.
Well, you initialize it directly from B, right? Okay.
And then the assignment, you're actually putting values into that space in memory, like a vector, you fill it with,
Right, but there's still a difference. And the difference is that initialization doesn't care of what the old state of the thing is, it initializes. Whereas assignment has to first get rid of the old state and then create a new state in it, which might seem superficial. But if you have a vector which is initialized to something very big, stores 1 million of integers, and then you assign another vector to it, you first have to release a memory for those 1 million integers, which you don't have to do in the initialization. So that's why initialization is different from assignment and is treated differently in C++. Okay? So initialization creates an initial state for a new object. Assignment first cleans up the old state of an existing object and then initializes a new state. In order for these operations to have correct semantics, we have to have equality defined, because otherwise we wouldn't know whether these operations are actually equivalent, right? So we have to have an operator equals that allows us to check whether A2 is actually the same as A1. Otherwise we wouldn't know whether this is a semi-regular type. Last but not least, even if you never call destructors, and I will talk about destructors in a minute in C++. In Java, they are called finalizers. They are kind of similar to destructors. I think Python had something like finalizers as well, right? So special functions that are being called when the object is going out of scope. Don't you? Oh, I might be wrong. I'm not that much of a Python specialist, but I know Java has finalizers. In C++, you have destructors, which are functions that are being invoked by the compiler whenever the object goes out of scope. And that is defined with a tilde and the type name. You never call them directly, well, almost never, but the compiler always calls them. So you can be sure that the destructor is being called. By the way, if at some job interview where you apply for a C++ position, the guy asks you, what is the most important feature for you in C++? There's one valid answer to that. And if you get that right, you get the job. What is that answer? It's destructors. Destructors are the most important feature in C++ from where I stand, and we will see a lot of applications for it in the future over the course. So just remember that. And if you do that, if you say that, you are always one step closer to being hired in that company. Generally, destructors end the lifetime of an object. So let's have a look at some arbitrary type. user-defined type just to see what are the different parts of it, and that's by no means everything. It's really just a very rough overview. The class definition starts with a keyword class or struct. Class and struct in C++ are almost the same things. What's the difference between a class and a struct in C++? Yes?
A class uses a pointer under the hood?
No. That's not correct. So a class doesn't use a pointer necessarily. You can have a pointer in a class, but you don't have to. Okay, any other ideas? Yes, please.
A class has methods attached to it?
Struct can have methods attached to it as well. So the only difference between a struct and a class, and that's the second question you might be asked in a C++ interview, is what's the difference between a class and a struct? The simple answer is there is no difference. Well, there's one difference, and that is default visibility rules. As you see, C++ has a public and private label-like directives inside the class, which tell the compiler which of those things are accessible from the outside by other code and which of the things are accessible only from inside the class itself, the private part. Now, struct has default visibility rules which are public, and classes have default visibility rules that are private. Otherwise, they are completely identical. That's why if it was class struct, I wouldn't have to write that public. I would get exactly the same semantics. Okay? So what we have a class definition which starts with a keyword, struct or class. We have definitions of, or declarations in this case, of constructors and a destructor. You can define member functions. You can do that on a struct as well. We can define operators, and we will do that extensively in many cases. And we will see how that works in the future. And you have some data that is stored in a struct or in a class to represent the state of that user-defined object. What do you need a type for? Why do you create types besides being able to reason about things? One of the reasons is that you want to make sure that you have more than one data element, in that case a, data, and member, that are always kept together, that are always in the same consecutive area of memory. They're always handled in one go. They are always referred to as a unit. And that's why you define a type. Okay. So let's extend the concept of semi-regularity by making the types regular. And the difference between regular and semi-regular types is that regular types know how to compare for equality and for non-equality. So we should define equal equal so that after constructing a copy, the original and the copy should be identical or equal. That's what I already said. By the way, if you define a equal equal, a comparison operation, and it returns something else, which you can do, you can let it return non-equality from the equality operator, or vice versa. And again, don't do that as long as you need job security. People will not be able to understand why the code is actually working if all the Boolean expressions in your code are inverted. And you can easily achieve that by just returning the wrong value from the operator you're defining. Don't do that. The world perishes if you do that, really. And kittens are being killed, which is even worse, I guess. So one important thing is that not equal should always, always, always act like not equal. And there's no reason for you to define both operators explicitly. You can always implement the not equal operator by writing this, and we will see how that works. So fundamentally, equal is a symmetric function, so we will implement it as a friend function on the types, and we will talk about what a friend function is in a moment. Last but not least, I want to make an even stronger create an even stronger type requirement, because a regular type you can't sort. How do you sort a regular type if you don't know what the sorting criteria is? How do you sort a regular type? Which of the things is smaller, which of the things is larger, so that you can put them in a sorted sequence? And that's why I want to make it even stronger and say, okay, I introduce a concept of totally ordered, which extends regular by adding a less than operator. Which means if I have two integers, I know exactly this one is smaller than that one. Less than must obey the following properties. Obviously, it has to be anti-reflexive. That means A is never less than A. Transitive, if A is less than B and B is less than C, then A should be less than C, obviously. Anti-symmetric, so if A is less than B, then B should not be less than A. And last but not least, if the things are not equal, then either that or that, less than or the greater than, should be true, obviously. So the semantics of less than must be totally bound to the semantics of all other comparison operations. Because only then we can write this kind of code. We can see that, okay, A larger than B, larger or equal to B, is the same as not A less than B. A larger than B is the same than B less than A. And A less than or equal to B can be expressed as not B equal less than A. And that is nice because, as you can see, we can write all the comparison operations only based on less than operation. We never have to come up with a special function that gives us the greater equal condition. We always can say, okay, greater equal is always not A less than B. And if you define these 6 operations we're talking about, comparison, equality, non-equality, less, greater, less equal, greater equal, if we find them in an interrelated way, we can be sure that we always get nice properties. And the world is round, everything works as expected. Again, same caveat, job security. So try to do something different here. Nobody will find the problems and they will have to rely on you being in the company because otherwise, well, nobody knows how to fix things. One aside, C++20 has introduced what's called the Spaceship operator. It's just less equal greater. And that's a nice thing because finally they have realized that it's because in the end you have to write 2 functions to have all relations correct, right? The equal and the less than. But why write 2 functions or even all 6 functions? Wouldn't it be nice if we were able to write just 1 function and let the compiler generate the other 6 functions from it as needed? So the Spaceship operator was introduced in C++20. It's a simplified way of writing relation operators for user-defined types. And instead of implementing all of these things, you implement one 3-way comparison function, which is that Spaceship operator, which returns something less than 0 if A is less than B, 0 if both are equal, or something greater than 0 if A is larger than B. So the other relation operators are automatically synthesized by the compiler, because the compiler can derive everything else from that Spaceship operator you define. And all you have to do in your class, you write auto operator, compare one x to another x equals default. And it will do what you want, because it will apply the Spaceship operator to all members in your class one by one. It's all you need to have a fully, totally ordered type in your user-defined type. Okay, any questions so far? Sorry about the theory. I know you're not here because you want to listen to a math lecture, but I think it's important to have that in mind when we talk about regularity. Any questions? Okay, let's go on. Singleton. If you look at the C++ standard and C++ as a language, you will see that C++ is an awfully complicated language. And if you talk to people, they will tell you, yeah, I'm doing C++ programming for 10 years and I still don't get it. Yes, C++ is a very, very complicated language. And the standard, C++ standard nowadays has 2,500 pages of describing how the language should work. Trust me, nobody, well, I know 2 people who know the C++ standard and understand everything in the standard. I don't, and I don't want to. Because Who wants to understand 2,500 pages of written in a very strange English, similar to English language, which I call legalese, which is weird language, which is, you have to really be a language lawyer to understand it. But I claim that you need only 5 pages from the standard to write good C++ code. So everybody can be an expert if you follow those simple guidelines. You don't have to know every depth of C++. And even more, it's good if you don't know certain dark corners about C++. If you follow the discussions on the internet, when people start get angry about C++ and start ranting about it, they always come up with something, but if I do this, then this bad thing happens. Well, the easiest solution is not to do it, right? But for that, you have to know what not to do. And that's a trick in C++. You have to know what not to do, and then you will be safe. And I will try to give you some of the hints and convey some of these things you should just not look at. And one of the things you shouldn't do in C++ is pointers. Never use a pointer. You will not need them, well, at least in this class, mostly. And whenever you see a pointer, a raw pointer, your alarm bells should go off. And you should be very, very careful. There are other rules, but that's the most important one. Pointers are evil. Don't use them if you don't absolutely have to. OK, so Singleton. What I will do, I will develop a simple type, a simple regular type, or even totally ordered type, which I call Singleton. Now, many of you might have read the Gang of 4 pattern book. So you might have heard about the Singleton pattern, which means have one instance, one global instance of a certain object and ensure that you don't have one, you only have one of those instances. This Singleton is not that. Don't confuse that with a Singleton pattern. The reason why I call it Singleton is because if you look at the dictionary, there's Singleton, pair, triplet, quadruple, and so on. And Singleton here stands only for a class that contains one thing, and one thing only. Okay? So don't confuse it with a pattern. So what this Singleton type I will develop is you can use it as a rubber stamp to create new types for yourself. Whenever you want to create a new type, copy that file, rename it, and add the stuff you need. It's that simple. So it's the simplest class possible, but it's the most complete class in a certain sense that is viable. An aside. On a very high level, this is the definition of Singleton. So you see the keyword template, then some type name T, the name of the type. This time I use struct because I don't want to have any visibility rules applied here. And it contains a single value of that type T. So you might get scared and say, hey, template, no, I don't want to work with that. Simply think about templates as type functions. In the same way as a normal function takes arguments and returns a new value, a type function takes types and returns another type. Nothing else. Okay? So it's a special kind of functions which operate on types and not on values. So you give it an int and it gives you an int pointer. You give it a t and it gives you a Singleton t. Okay? So we want to have something which takes one type and returns another one, a type function. So the template mechanism in C++ is just that, nothing else. In that sense, a vector t is just a type function which takes an arbitrary type t and gives you back a container that can store t's. Okay? It's just a type function, nothing else. So the simplest example is, as I said, integer star. It's a function that returns a pointer from an integer. So it transforms one type into another type. So our Singleton is a type function that takes a t and gives us a Singleton t. Just think about it that way. That's all. Okay. Let me skip that. Let's do another aside. one thing you have to know is that whenever you create a user-defined type in your code, the compiler generates 6 functions for you. Those 6 functions are guaranteed to be there as long as you don't define them yourself. So that empty Singleton template I gave you will have 6 member functions defined by default. They're there. And those 6 functions are always available, and that is a default constructor. It's the function that is being invoked whenever you define a new instance of that type without any additional arguments. It default initializes that thing. So if I write TA semicolon, the default constructor for T will be called. The destructor, it's a function that is being invoked when the type goes out of scope, when it's being destroyed, when it ends its lifetime. Copy constructor and copy assignment are the 2 things we need for our regularity, right? We talked about that. Copy construction is copy initialization, and copy assignment is the assignment to establish equality. There are 2 more functions, move constructor, move assignment. I will not talk about those at this point because they go a bit beyond what we want to actually talk about with regular types. So let's ignore them for now. Think of these 2 things as special versions of the copy constructor with some bells and whistles attached. Not significant here. So these special functions are being automatically used in the appropriate context. And the compiler-generated functions simply apply its own operation to all members, one by one. So default constructor for a type, if you don't define it, the compiler will synthesize the default constructor for all members and call them in sequence. That's it. Unfortunately, the Spaceship operator is not predefined. You have to be explicit about it, which is an oversight, I think. They should have made that into a 7th compiler-generated function. But here we go. Okay, so let's have some examples. Constructors are special functions that automatically are used automatically whenever a new instance of a user-defined type is being created. The default constructor is the one that is used whenever you don't specify any additional arguments here, right? S is just initialized using its default constructor. The destructor is automatically called whenever an instance goes out of scope. The copy constructor is being used whenever you copy initialize something, and the copy assignment operator is used whenever you copy assign something. So there is a way for you to actually define the semantics of that thing. You can write a function which does that. But if you don't, the compiler will just do what I said. It will synthesize a function that will call the appropriate operation on all the members one by one. So any compiler-generated function by default invokes the corresponding special functions for all members. For instance, the default constructor invokes the default constructor for all members in the sequence of their definition. All operators, all compiler-generated functions do it in the sequence of definition of the members, except for the destructor, which invokes the destructor in the reverse order, because you want to destruct things in the reverse order they were constructed to maintain dependencies. So let's implement support to make a singleton semi-regular. Well, I define a default constructor, doesn't do anything. I define a destructor, which doesn't do anything, obviously. I create a copy constructor, and this is the prototype you always used for copy initialization. It's a constructor, and you note that constructors don't return a value and have the same name as a type. So you can define your own constructors by adding a function to your type that has the same name as a type itself and doesn't return a value. And that thing is a constructor. Here's the copy constructor because it takes one argument which is of the same type of whatever the thing you want to create, and that is the usual semantics. And all what we want to do in our case is to copy the value we have in our singleton. That's all we want to do. The assignment operator looks like this. You have an operator equal. Right-hand side is the same type as the type itself. And all you want to do, you want to assign the value from the right-hand side to yourself And the only trick here is it returns a reference to the type. Why do we do that? Why does the assignment operator return a reference to the object that is being assigned to? Well, the answer is very simple. Let's say I have 3 things of type type T, and I want to write A equals B equals C, which is valid in C and C++, right? You can assign integers that way, which means that C is being assigned to both of them, which in the end by the compiler is interpreted like this. It first assigns B to C, and then whatever that thing returns is assigned to A. But what is that thing it returns? It has to be a reference to B in order to function correctly. That's why the assignment operator always returns a reference to the type and returns a star this. So return a reference to myself so I can be used on the right-hand side of assignments. Okay? Well, as I said, we don't have to write these functions at all because that's what the compiler would synthesize anyway. But if you want to be explicit about things, you can also do this. You can tell the compiler, hey, I want to have whatever you would generate for that function by saying equals default, which is always a good idea to do because it gives you certainty of what actually is happening. Okay? By the way, I just had a bug to be fixed where I had a constructor equals default and it was doing the wrong thing. So be careful with that. Always be explicit. Okay. So what we have, or what are the semantics of the default constructor? We want whatever the default value of T is to be assigned to the value that is stored in the singleton. But that's what the compiler anyway is doing, right? I said it will invoke the default constructor for all members. So it will default initialize T in our case as well. So one caveat, I said that default constructor is always being synthesized. That is true only as long as you don't write any other constructors yourself. If you write any other constructors, the default constructor will not be synthesized, which is a very weird rule. People have come up with that rule 20, 40 years ago, I don't know. So always be explicit and define a default constructor, even if you don't have any others, just to be sure that the default constructor is available. Last note, you might have heard that C++ has virtual functions, and especially people that come from Java like virtual functions because everything in Java is a virtual function, right? If you have a derivation chain and you call the base some function which is overloaded in all derived types, and you call the function on the base class, the most derived version of that function is being called in Java, which is essentially what a virtual function does. So the question is, some people believe that destructors should be virtual, which is the wrongest thing you can think of. Try not to make a destructor virtual as long as you don't have any other explicit virtual functions in your type. Don't do that. It just creates overhead, creates a lot of messy code. So if you want to prevent any problems that could come from non-virtuality of the destructor, just make your type final, which means that users can't derive anything from it anyway, which is okay in our case because there's no point in us deriving anything from Singleton anyway. So let's make it final. And that solves the issue of the virtual destructor just fine. Okay. Any questions so far? No? I'm almost done with theory, so you can start waking up because things start becoming interesting. Let's make it regular. So what we need to do in order to make Singleton regular, we need to define the equality operator, which we do this way. Friend, bool, operator equals, left-hand side, right-hand side, and we compare the value. What is a friend function? A friend function which is defined inside a type, which is not a member function, but it has access to all the private data of that function, of that type. You can simply remember it by thinking about what is a friend. A friend is somebody who is allowed to touch your private parts. Okay? So in that sense, friend is a function that is allowed to see the private members of a class, even if it's not a member of the class. Okay? And it gives you symmetry, because you can always write x equals y, and both are treated the same. If you didn't implement that as a friend function, but as a operator that takes only the right-hand side, you would get a unsymmetric way of invoking the assignment. So these relation operators are usually implemented using friend functions anyway. Let's reason about equality a bit. What does it mean, equality? Well, I already said it. Equality implies that there's a law of identity. A is always equals A. A law of non-contradiction. So if A is equal to B, then it can't be non-equal to B. And excluded middle, if P must be either true or false, right? It's either equal or not. You're either pregnant or you're not. It's that simple. There's no middle way. Which is true for integers, right? I have an integer. These laws are true. If I have two integers, a and b, they're either equal or not. That's the truth of it. I said that all built-in types actually are regular types. Can you think of a built-in type that is not regular? What built-in types do we have? We have integers, we have chars, we have shorts, we have longs, we have doubles, and we have floats, and bools. Which of those are not regular, and why? That's the exercise. Figure out a type that violates the law of identity. A type for which the fact that x is equal to y does not imply that x is not equal to y. Can you think of a type for which that is true? Yes?
Is it floats?
Floats. And why?
Because floats have not a number.
Right. Floats are a representation of floating point numbers in memory. They're usually 32 or 64 bits long. And the bit patterns representing the mantissa, the exponent, and the plus, the two signs on the mantissa and the exponent, are such that not all bit patterns that you can store in a 64-bit value give you a valid float. Because not every bit pattern is represented by a valid float. And the standard, the IEEE 754 standard that defines what a floating point number is, says that you get these bit patterns when you do division by zero, or if you have infinity, or these kind of weird corner cases which are not valid floats, but you still want to be able to represent them. And that's why the floating point standard introduces something which is called NaN, not a number, which is a bit pattern in a float which is not a float, because it was a product of a division by zero or some infinity or whatever. Now, how do you detect whether a floating point number is and not a number? How do you do that? Well, you do it this way. If x and y, or if x is not a number, I'm sorry, my pen doesn't work. Okay, what happened? X equals x and x not equal to x. If this is true, then x is not a number. So it's both. It's not equal, and it's not equal. So in other words, floating point numbers, reals, floats and doubles, have these weird things, the weird state that formally makes them non-regular, because our laws are not true anymore. But since not in numbers or infinity or division by zero is something like an exceptional case, people tend to ignore that. And if you ignore those bit patterns that are not a number, then double is a perfectly nice regular type. Okay? Where are you? Okay, so now let's make Singleton totally ordered by defining these 4 as relational operations: less than, greater than, less equal, and greater equal. And as I said, all we have to do, we have to implement one of those, and the others are derived from it. So we have to implement only one of those functions, and these 3 functions are always the same no matter what you do. You don't even have to think, you just can copy-paste these 3 functions, and you will always get the right semantics. But even simpler, it's certainly if you write the Spaceship operator, because then you don't need any of the 6 functions. You just write that one function and you're done with it. Please note that it doesn't return a bool. It returns something else. It returns some special types that represent the 3-state thing. And you can encode strict ordering, weak ordering, and other things. And we might talk about that later. But for now, just remember that the Spaceship operator always returns a computed type, and we don't care what that type is. But even better, why don't we write it this way? Why don't we just say, hey, please synthesize that thing for me, because it's exactly what I wanted. So the Spaceship operator should have been part of the language forever. It was added only a couple of years ago, and should be synthesized by the compiler, by my opinion, the same as the 6 predefined functions, but it's not synthesized for you, so you always have to write essentially that one line in your types. Okay, so let's put everything together. We said our Singleton should be regular, semi-regular, or totally ordered. When is our Singleton regular? Well, it's regular as long as T is regular. It's semi-regular when T is semi-regular. And it's totally ordered when T is totally ordered. And in order to make sure that I use Singleton only with one of those 3 type properties, type concepts, I add a special concept check on the template, which C++ allows you to do, which says, please use this type only as long as T is the regular, semi-regular, or totally ordered. And as you see, these 3 concepts are predefined by the standard library. So you don't have to worry about how to implement those themselves yourself. You can just use regular, semi-regular, and totally ordered as predefined things from the standard library, which makes sure that our Singleton will work only for these 3, as long as T is one of these 3 groups of types. The only thing you might wonder, we have defined the assignment and the ordering operators always. How does it work if I plug in only a semi-regular T? Wouldn't the other functions be invalid? Wouldn't I get a compilation error? Well, not. Because templates have the nice property that they only instantiate things that are actually needed. So you will not have any problems with that. Just as an exercise for you, create your own user-defined type, but don't make it Singleton that stores one thing, but make it a pair which stores 2 things. And try to implement it yourself and try to experiment with it. I'm not going to do it here, just for you to play around with it, to get a feel of how easy it is to create a user-defined type. It's trivial. And by the way, that Singleton header file is linked from the lecture slide, so you will find a repository where you can just copy-paste the Singleton implementation completely, and you can play with it. Okay. Perfect. Instrumented. As I said, I want to prove to you that I was right in the first lecture, because some students just don't believe that using a standard set to store all the integers is much slower than using sort and using a special algorithm which is called unique to find all the unique elements in a sequence. So we will write a adapter type, which we call instrumented T, it's a template again, which will take a T and behave exactly like a T. But in addition to behaving like a T, it counts all the operations on that object, on that instance. So that means we can use instrumented T's wherever we wanted to use the T itself. We can pass them to our functions, we can pass them, store them in containers, we can do all the operations. And that's another benefit, right? We know it's regular. And we know that containers can handle regular types, so we don't even have to think about it. As long as we instrument it in a proper way, we know we can do everything on an instrumented T, what we would be able to do on a T itself. So just in addition, it will count the operations, and that will be very useful because it gives us a means of measuring performance. And this course is all about parallel computing. And how do we know whether our parallelization is actually efficient? We need to be able to analyze performance. And I'm just giving you one tool you can use in your toolbox in the future just to assess performance of the code you're writing. Which operations will we count? Well, the ones that make it regular or totally ordered. All the operations we just defined. So we will redefine all the operations I had. The copy constructor, assignment, default constructor, destructor, and so on, in the same way as we implemented them in Singleton, but additionally we will just increment a counter, which tells us how often that function was called. So it will teach us how to write a regular class. What do we do with all those counts? Where do we store them? Well, what I suggest is we create a simple class that contains an array of counts, one count for each of the operations. One for copy, assignment, destructor, and so on, and some enum that we will use as the index into that array so that we know that we get the right count and we can reason about the code afterwards. Please note that all these things, all these three variable definitions are static. Static means they don't belong to the class and they exist only once for the class. So it's like class members in Java, I think. When you static in Java, it's the same thing, right? It exists once for all instances of that class. Same thing is here. So static variables means it exists only once for all instances. So if you have 10 instances, we still have only one array of counters, which is exactly what we want. And then we derive our instrumented from the instrumented base. And otherwise, it's very similar to the Singleton, right? We just added that base class. And please note, since the base doesn't add any members, it's empty. It's an empty type. It has only statics. The size of an instrumented is the same as the size of a T, which is sometimes important, right? It requires exactly the same amount of memory to be stored as the original T. It will not have any more data stored in memory. All it does, it adds additional functionality on top of it. Okay, so copy constructor. Instrumented on the right-hand side, we want to initialize our value, obviously, from the right-hand side. But in addition, we count the copy operations. The default constructor. All we want to do in addition, we want to count the number of operations, how often is that function being called, and so on and so on. So you can kind of see the trend. Okay, so just to repeat what we had the case that we have a sequence of integers, and we wanted to store those sequence of integers in a set of ints, and then print the number of those integers in the set. But instead of having a set of ints, we now have a set of instrumented ints. And instead of a set of a vector of ints, we have a vector of instrumented ints, nothing else. And it will compile just fine. There's no change needed. You just replace whatever type you want to instrument with the instrumented of that type and be done with it. So this was one use case that was using the set. And this is the other use case where I said, okay, it's much more efficient to first sort our sequence and then apply an algorithm unique, which reorders things in a way so that all unique elements come first. And it returns the reference to the first non-unique element. So if you take the difference between the whatever it returns and the beginning of that sequence, you get the number of elements that are unique. Again, I'm using instrumented int, and as you can see, I can just use a normal standard sort. It just works. Also, what I want to do, I want not only to count operations, I want to measure how long does it take. And for that, I want to introduce a simple class, which is, by the way, regular as well. So it's taken from the Singleton, just not a template, because we don't need a template at this point. But the idea is the same. And that type has a stores start time and stop time. It has a default constructor. It has two functions, start and stop just asks the system, what time do we have, and stores it in the two variables. And it has an elapsed function, which takes the difference of these two time steps and returns a number of milliseconds to you. Okay? Very simple class. And you can use that class by just saying, create a timer, start measuring, then do the stuff you want to measure, then you stop measuring, and then you print the elapsed time afterwards, which gives you the last difference between the last stop and the last start. That is the other piece of code I just applied to the experiments I did. Any questions about that? Should be easy enough. And you will use that in your homework, by the way. Exactly that class is something you can use in future assignments. And again, I will provide you with the full code of that thing, so you don't have to copy paste it from anywhere. Okay, so this is the data I collected from the first version, from the standard set, where I just incremented the number of elements in the integer from 16 to 8 million. And those are the counters of the operations: copy, assign, destruction, default construction. No equality. Equality was never called, but less than was called about 300 million times to insert 8 million elements in a standard set. 300 million times. And the last column is the time in seconds. So you see that for 8 million elements, that algorithm I had takes about 15 seconds to execute. Just remember these two numbers, 300 million, 15 seconds. If you put that on a graph, note that the brown line is the time on the right axis. The others are the counts and are on the left axis. So as you see, the less than operator is the prevalently used operation. It's the light green one. And as expected, the time is logarithmic, right? It goes slightly up. So it's n log n as we would expect. Okay, now let's look at the same for the unique. Here's the same for the sort and unique. Again, 8 million elements, 430 million comparison operations. So 50% more, right? We had roughly 300 million before. Now we have 430 million operations. But the overall execution time is 1.8 seconds. Okay, which is kind of counterintuitive. We do more work, but we run 10 times faster. Isn't that unexpected? So let's look at the graph. Again, brown is the time on the right axis. The rest are the counters on the left axis. And you see that there's much more spread in terms of operations because some of the other operations are called much more often than in the first case. Just to compare it a bit closer, this is a number of comparisons. The orange one is the set, and the unique one is the blue. Blue is the unique, and you see about 50% more operations. But if you look at the time, you see the opposite trend. The set has a lot of, well, took 10 times longer than the sort and unique. You might say, well, this is not logarithmic. Well, it is. It's just much slower. So it seems to be linear, but it isn't. It grows faster than linearity. Okay? Why is that the case? I'm doing much more work, but I'm running 10 times faster. What do you think?
Parallel computing.
There's no parallelism. It's all sequential. It's all the same core, same machine, one thread. Yes?
The set is performing other operations
For instance. No, a set is just a tree. Just a binary tree, nothing else. But you're right, it has to reorder the tree on each insertion. So there is some hidden operations because it has to reorder the nodes, right? So there's that, yes. What else? Yes?
The operations are less intensive.
They are less than what?
The unique and sort operations that it's doing are less intensive.
Well, it's the same comparison. It's the same instrument that I'm using. It just compares two values, nothing else. Two integers. Yes?
The unique sort is taking better advantage of cache.
Absolutely. That's it. That's what I said in the first lecture. If you have to choose a data structure, what do you choose? What container do you choose? Well, there is no question. Standard vector. End of story. And if you believe that you should use something else like a standard vector, think again and use it anyway. Okay? And the reason is standard vector places all elements consecutively in memory, whereas a standard set distributes that arbitrarily across a memory, right? Each node is allocated independently and might end up somewhere. And that means that when you might know a bit about caches, and we will talk about cache structure and so on. The memory access to in modern cores happens based on cache line, on the length of cache lines. That means that every read doesn't actually read just the byte you want to have, but it reads 64 bytes that are adjacent to the one you need, and put those 64 bytes into the cache. Now, the access time to the cache is about 100 times faster than the access time to the external memory. That means if you refer to the first element in your vector, it also loads all couple of consecutive elements right away into the cache without additional timing requirements, because it loads 64 bytes anyway. That means that when your algorithm goes through your data sequentially, the next value is already in the cache, so that the data access time to that next element is much, much faster compared to what you would have to do when you traverse a set. Because in a set, you don't have that cache locality, you don't have that spatial relationship between neighboring elements because they are distributed all across memory. So to do some conclusions, and then I'll let you go. Even if the number of operations is larger, the code may run much faster. In other words, the textbook solutions you have are mostly wrong, because those textbooks were written for computers that we had 15 years ago or 20 years ago. And as you know, those textbooks have usually 10th edition, 20th edition, whatever, and all the author has done has kind of tweaked it here, corrected some typos and so on, and has never actually thought about what the computer science background has actually transformed over the last 15 years. In other words, understanding computer architecture is absolutely critically important, and we will highlight that in these lectures over and over again, and I will talk about architecture and memory structure and these things all the time. So if you want to write efficient software, you have to understand what your architecture is doing, right? If you want to drive your car efficiently, you have to understand how the car works. Same thing here. If you want to write efficient software, you have to understand how your computer works. On the other hand, understanding big O is equally important, right? If you have two algorithms and one has a much worse big O complexity than the other one, you know which one you have to choose. Last but not least, all depends on the used data structures and how well these are aligned with the computer architecture. As I said, always use standard vector. There is no question. Whenever you have to select a container, stop thinking, use standard vector. And if you still think that you need something else, think again and use it anyway. And there are always ways around that. We can always go back to a memory layout that all elements are consecutive. And even the standard library even gives you adapters, which is called a flat set, for instance, which takes a vector and constructs a set on top of that vector, which gives you almost the same performance as the unique, sort and unique, because the data is aligned consecutively in memory. Okay, so an exercise for you if you want to. Measure and compare the amount of operations on and the overall execution time for some standard sort or some stable sort, and try to interpret it. Explain what you're seeing. Explain it to yourself. If you wish to submit that, I'd be happy to give you some extra credits. There will be always exercises in these lectures, and whenever you see an exercise which is not explained in lecture, feel free to do it. Send it to me, and we will negotiate on how many points I will give you, okay? In summary, we know that Singleton T and instrumented T conform to the type requirements that are all standard containers and algorithms expect. So that means these two types we can use anywhere where it was valid to use a T, which is important. This guarantees that the types can be used with all algorithms on containers, with all of the standard library. This will not change the semantics of the algorithms. Right? We were using std sort just with a vector of instrumented ints, without changing the semantics of that sorting. So the understanding of what concepts are assumed to apply for a given function or data structure is important. Always try to understand what are the type requirements of that function I'm writing. What properties does the function expect for the arguments to have? And that's what I meant in the beginning. I want to write software that is correct by design. And one way is to think about the type properties of your arguments for functions and see if those type properties influence the operation of the functions. And what are the minimal requirements for those types I'm using for my function. And last but not least, if a function or data structure works with a type that conforms to a set of concepts, I can be sure that it will work for any other type that conforms to that same set of concepts as well. And that is one of the fundamental insights I want to convey. Once you know that something works for a certain set of type properties, you can be sure that it will work for any type that exposes those properties. Which might sound trivial, but it's one of the most fundamental insights I can teach to you in this class, as strange as it sounds. Well, on this, I'll let you go. Thank you so much for your attention, and see you the other day, on Thursday, I guess.